Welcome, this is Mr. Hacker. This is my first attempt at doing one of these ChemCast videos, so please bear with me. I'm just up here, in my room, so if you hear any weird noises or anything, I'm probably not going to stop. I'll probably just go on, so, just ignore them. I would strongly encourage that you take notes as you go along and watch this. These are things that I'm going to expect you to know. Since these are presented to you, in this format, this gives us more opportunities during class time to work on problems or answer questions. So these will be some of the kind of mundane notes and some of the, the simple explanations. So we're going to go ahead and begin. This lesson is about significant figures. You may ask yourself, what are significant figures? Basically we talked yesterday about errors in measurement and how precise you can measure using certain devices and so forth. Significant figures really deals with measurements and mathematical calculations using measurement, and the main goal is to make it apparent to other people who will see your work later on, that maybe weren't present when you took the measurement, and tells them basically what you measured with, how accurate the measurement is. So you'll see in this first example, I have a little nubby pencil here, just to kind of demonstrate significant figures and what they aren't. Let's say I wanted to find the length of this pencil, and you'll notice I have the centimeter ruler there below it. And let's say I'm going to read just right to the end here, and let's see, it's 2, it's greater than 2 but less than 3, and then notice each one of the little unit markings are tenths of a centimeter, or really they're millimeters. So there's 2, 2.1, 2.2. It's greater than 2.3, but somewhat less than 2.4. So if I were to write like 2.3, 7, 9, 8, 2, 5 centimeters, if you stop and look at it, that number looks kind of ridiculous, and it is, because there's no way that I could measure to the tenths, hundreds, thousands, 10,000s, 100,000, the millionths of a centimeter using just my eyeballs and that centimeter ruler provided. So yeah, this would not be an example of a good measurement to take, significant digits. Okay, but what we can do with this measurement, if you look, okay, there's 2 and then 0.1, 2, 3. So 2.3, and then remember there are no moving parts on a ruler, so you must estimate 1 decimal place past the smallest unit marking. Since the smallest unit marking is the tenth of a centimeter, I can estimate to the hundredths. And just so you know, that last place is an estimation, so it's not an exact number. Two people looking at the same thing are going to do it in a different way. So just me eyeballing it, and this is, a ways off, I'm going to say maybe it's 2.33 centimeters. Notice I use the unit label. Maybe another person would say 2.32 centimeters. Maybe somebody sees it and says 2.34 centimeters. Which one's right and which one's wrong? Well, they're all right. That last digit is an estimate, and, the first 2 digits are the same. And so therefore any of them could be considered valid. And what this tells me is that this measurement was taken, and that it was accurate up to the hundredths of a centimeter. So that digit is the one that was estimated. Okay, on this slide you're going to notice that I have 5 typed up rules. These are just the general rules for counting significant figures, so we're just going to be looking at measurements or looking at numbers and identifying how many significant figures count in these numbers. So largely we'll utilize this knowledge later on for doing mathematical calculations and so forth. But what I want you to do at this point, I'm not going to sit here and read them all to you. Just go ahead and pause the video, go ahead and copy these 5 rules down. If you don't understand them right now, that's fine. I'm going to go ahead on the following slides, and I'm going to give you examples and kind of explain each of them. So as you're copying these down, go ahead and pause, because I'm not going to sit here and hum a tune for you or something as you copy these down. All right. Okay, the first rule states that all non-zeros are always significant. So any number that is not a zero counts towards significant figures, or sig figs. So in this first measurement, you'll notice it's 28.4 feet. And so all three of those digits are non-zeros. So this guy has three, oops, I didn't have the pen selected there, I don't think. Well, maybe I did. 3 sig figs. That's another way you will see me writing significant figures, all abbreviated sig figs. You may also hear these referred to as significant digits. So 28.4 feet has 3 significant figures. The next measurement, you'll notice 7 meters. Okay, in this case, there's only one digit, so obviously it has 1 sig fig. The other thing, I want to mention to you is, kind of stop and think what this means. So 7 meters, only written as 7 with no other numbers. This tells me that really this measurement is only accurate to 1 meter. So in reality, that means that this measurement could really be anything between 6.5 meters all the way up to 7.4 meters. So we're talking plus or minus, a meter. It's somewhere in that range. But this is accurate as this measurement has been made. It's like if you ask me how tall is that flagpole. Me just looking at it, I could estimate, it's 7 meters. Is it exactly 7 meters? Did I get up there and measure it with a tape measure or with a meter stick and move it a number of times? Well, probably not. So the way I reported that answer, that's telling me that there is some, leeway, some error in there, and it could be plus or minus, but I'm only accurate to the meter. This last number you'll see on here, this would be like an example. If I asked you the population of Omaha, and they do a census and they go around door to door and they count people, and they say there's 327,689 people that live in Omaha. So because all of those digits are non-zeros, this one would have 6 sig figs. The next rule states that zeros appearing between non-zeros are significant. Here's an example, 101 Chihuahuas. This could be maybe a knockoff of some copyrighted Disney film. But in this case, you will notice 101 Chihuahuas. So obviously, we know from the previous rule that the 1 in the hundreds place and the 1 in the ones place are both significant. Notice the 0 appears between them. That means that 0 is significant. That would represent like 10 Chihuahuas. So in this case, since we know there's 101, it's accurate to 1 Chihuahua. So in this case, this number, why does it do that? I don't know. Let's see if I can prevent that from happening again. There are 3 sig figs present in 101 Chihuahuas. In this example, I have 103.7 degrees Celsius. Once again, the 1, the 3, and the 7 are obviously significant. The 0 is a placeholder because that's measuring 10 degrees, and we're accurate down to the 10th of a degree. So definitely that 10 degrees is spot on. So this number would have 4 significant figures. This last measurement, 12.006 kilometers. Okay, now notice this time there might be some question because you're like, well, in the other two, there was a non-zero on either side of the 0, right? But in this case, I have 2 zeros back to back. That doesn't matter. Those zeros are still between the 2, and the 6. So here's the 2, here's the 6. They're between there, so they count. So in this case, 12.006 would have 5 sig figs. The next rule is one that, sometimes upsets people when they see it. It states zeros appearing in front of non-zeros are not significant. In some cases, it kind of makes sense. A lot of times you're not going to see zeros that occur in front of just like regular numbers. Nobody would write the number 1,000 with 0 100, okay? That's generally not very common. Generally, if there are going to be what are known as leading zeros, more than likely there's going to be a decimal point that is involved. So in this first case, you'll notice we have 69 cents. Okay, that zero, it comes before a non-zero. I mean, it's to the left of any non-zero, and so therefore it does not count. 69 cents only has, I think I'm going to do that on every page, so I guess you might as well just get used to that little thing swirling. Hopefully it doesn't record that, and maybe if you don't see it, you'll be like, what is he talking about? But as I'm writing it, it moves the page around unless I click on the, I have to click the pencil each time, I think. So anyway, 69 cents would be 2 significant figures. Okay, in this next example, okay, 0.001 grams. So we're talking tenths, hundredths, the thousandths of a gram. Notice all of those zeros precede the first non-zero. They do not count for significant digits. This number only has 1 sig fig. And I know that upsets people because, you know, you look at that and you're like, well, I mean, they have value. They're placeholders. Okay? Hopefully I can explain it here with this next example, and hopefully you will see the fact that, you know, how this whole thing works. In this last measurement, I have 0.0025 kilometers. Okay, so once again, those leading zeros don't count. So in this example, this number would only have 2 sig figs. So back to what I was kind of alluding to here on this on the previous problem. Those zeros aren't really measured. Okay, you look at it, it's like, how can they not be measured? Well, if you stop and kind of think about what that number is and what it represents. So we're dealing with tenths, hundredths, thousandths, 10,000ths of a kilometer. Okay, so the thousandths of a kilometer would just be a meter, right? Because a meter is, or 1,000 meters is a kilometer. So 1/1000th of a meter would be, of a kilometer would be a meter. So in this case, what this number is really representing would be 2.5 meters. So really you're measuring, this is telling me I'm accurate to the tenth of a meter or a decimeter. Now you may be saying to yourself, you know, self, why on earth, if you're measuring something that's only like 2.5 meters wide, why would you put it in units of the kilometers? You know, that just doesn't make sense. Well, you may be using this in some other math problem where maybe you're trying to calculate the surface area of, I don't know, like maybe a sidewalk. You know, maybe a sidewalk is poured and it's, 2.5 meters wide, but maybe it's several, kilometers in length. In order to combine those two units, you need the same number, the same units associated with it. So, when you could choose to put them both in kilometers and both in meters, I guess it wouldn't really matter either way. But the thing is, what I'm trying to explain to you is that this is telling me that I measured to the tenth of a meter or the decimeter in this case. So only two significance or two of those sig figs are significant. The other zeros are just placeholders. This rule states that zeros at the end of the number and to the right of the decimal point are significant. So in this first example, let's say I have a measure of 12.00 meters. All right, this may be like the height of maybe a high diving board. I mean, that'd be a pretty high diving board, but let's just say for our example here, this is a really high diving board, 12.00 meters. Okay, these zeros, because they are at the end of a number and to the right of a decimal, that means that they are significant. So this board has been measured to the hundredth of a meter, which would be a centimeter. So this thing is accurate to the centimeter. That is 12 meters to the centimeter. Okay, it's not an estimate where somebody just eyeballed it and was like, that board looks to be about 12 meters tall. No, they said 12 meters, 12.00. This is accurate to 1 centimeter. So this one has actually 4 significant figures. All right, and you may say, I understand why the one at the very end, but why is this 0 then significant? Well, the one at the end we know because it's at the end of the number and to the right of a decimal, and then therefore if this 0 is significant and these are significant, this 0 is between them, therefore it is significant. All four are significant. Likewise, I measure the mass of some objects 6.030 kilograms. Once again, you know the 6 and the 3 are. The first 0 is significant because it is between non-zeros. The 0 at the end is significant because it's at the end of the number and to the right of a decimal. So therefore this guy has 4 sig figs as well. The last example we have here is $20. And notice the way I've written it, 20 with a decimal and 2 zeros. This means a $20 bill. It is exactly $20, accurate to the penny, and that's as accurate as our monetary system goes, is to the penny. We don't have half pennies or so forth. And so if you're asking your mom for $20, be specific, because if you just say $20 and you say it like this, can I have $20? Technically that would be only one sig fig, so she could give you anywhere between $15, or I guess maybe on the good side she could give you 24. But no, 20 written this way, that 0's at the end of the number to the right of the decimal. The other 2 zeros are between the 2 and that significant one. This one also has 4 sig figs. Yay, we made it to the last slide. All right, thanks for hanging with me here for this first ChemCast video. You'll notice this rule, this one's kind of ambiguous. It leaves a little room for interpretation. It states 0's at the end of a number and, without a decimal point, may or may not be significant. The big problem or with this is that you don't really know if it's significant or not. So usually a decimal point is going to be placed after zeros if they have been measured or estimated. So in this example, let's say the way we have this written, there are 6,000 people that live in the city of Ralston, Nebraska. The way I have it written, according to the significant figure rules, you will notice there is no decimal point. If I had you look at this number, I would say only the 6 is significant in this case. And once again, I am moving. All right, let's try this one more time. Nope. Once more. There we go. All right, that 6 is significant. But the zeros in this case would not be. So 6,000 written 600. I would say it has 1 significant figure. Now, maybe when they went around and they did the census and they went door to door and counted the people, and there were exactly 6,000 people. I mean, to the person. They knocked on every door, and there just happened to be an exact even number, like 6,000. The way that you would record 6,000, showing that you measured and it is exact to the person, is you would place a decimal. So this would be 6,000 people accurate to the person. This one would have 4 sig figs. Now likewise, you may say to yourself, what happens if, it was accurate to like maybe 100 people? There's generally 2 ways you can do that. You can't write 6,000 and put the decimal behind the first 0, because then it would be 60. It wouldn't be 6,000. So if I wanted to represent the number 6,000 with 2 significant figures, so showing that it was 6,000 accurate to 100 people, you could do it in one of 2 ways. Probably the most common way would be by using scientific notation. Now we'll get into this, probably in the next lesson, probably tomorrow during class. But the way you would write this number 6,000 with 2 significant figures is you'd write this as 6.0 times 10 to the 3rd power. And we'll talk about this later. Don't, get all upset that I'm using scientific notation. We'll get to that. There's another way you could write it. This way is less common, but you could write 6,000 people, and you could put like a line above the one that was measured. So this tells me 6,000 people accurate to the 100. So All right, well, I hope you learned something. And if you have questions, come with them tomorrow. And have a great night.